All right, so this is discussion week 6, problem 3, and it's a roller coaster. You're told that you start in the roller coaster at rest at 80 meters above the ground. You come through and there's a loop-de-loop that has a radius of 20, so I drew it here as having a total height of 40. And you want to find, so you're imagining that if you were sitting on a scale in this roller coaster, what would that scale read when you're at the top of the loop-de-loop? And so this is a two-part problem. The first part we want to do is we want to find the velocity when you're in that loop-de-loop. And so what we're going to do is we're going to use conservation of mechanical energy. Why can we use that? Because only gravity is doing work on this roller coaster car. So we're told that assume it's a frictionless track, and so as this is sort of like these bobsled problems or something we've been doing. So as it goes through this track, if only gravity is acting, then we can use conservation of mechanical energy. And so I'll say mechanical energy final equals mechanical energy initial. Now I have the freedom to do whatever I want, so I'm going to call right here to be my height 0, which means that over here my initial height would just be 40 meters is how you could set that up. So we assume that it's at rest. So initially it would be mg, again I'm calling h initial, and then my final mechanical energy would just be 1/2 mv squared, because my height, so since I called this to be 0, the height when you reach that final point is 0. You don't got to do it this way, but it just kind of works out nice. And so I'm going to go ahead and cross this stuff out, these m's here, and then go through and just say that, okay, so v squared then, if I do this, it's going to equal 2g hi square rooted. And so that's my velocity. Oh, excuse me. I kept it in v squared. And why did I do that? Well, because I'm going to be doing centripetal acceleration. So it's just kind of easier to plug that in. And so now we look over here and we say, okay, so what are the forces that are acting on this roller coaster car? So this is, again, similar to some other problems that we've done. So if you look here, I'm going to say there's a normal force of the track pushing on the roller coaster. There's mg, gravity pulling down, and that should be the only two forces. So lots of different ways to do this, but I'll just do my typical calling this to be the positive y direction. And so this is, I can do my sum of the forces in the y direction, and in this case, my centripetal acceleration, right, is going to be pointing in towards the center of the circle. And so it's one of these cases where I'll say negative Fn negative mg equals negative m v squared over r. And of course, since these are all negative, I can just multiply by -1 and make them all positive, just to make life a little bit easier. And so we get here the normal force equals mv squared divided by r minus mg. And again, the normal force is what we're looking here for, right? So basically, you know, that normal force, if you're sitting on a scale, that scale basically tells you how, you know, hard you're pressing against that scale, right? Normally it's just because of mg, but in a situation like this, right, you'd have a case where it could read more than mg or less depending on what's happening in the circumstance. And so if you look here, so this would be our equation, which we've gotten similar ones to this on similar sort of situations. And so now what we want to do is we want to plug in this v squared. So we'll say the normal force, which again is what we're looking for. And so I'll say m, and so for v squared I'll write 2g hi, again, over r minus mg. So a couple things here that we're going to clean up is we're just going to say that, you know, this problem wanted you to find things in terms of the weight. And so the weight of this person, right, is mg. And so it's the m times g. So we're sort of doing this on the person sitting in the car. So I can clean up this equation a little bit. Wherever there's an mg, putting in a w. So here it'd be like w and then 2 hi over r minus w. And so now we just got to figure out how to relate hi to r. So if you remember, hi was 40, and if you remember in the problem, r, the radius here, is 20 meters. So hi over r will be 4. Okay, so I can say that my height initial over the r, and that's just, again, due to how we sort of set up our roller coaster. And so if I do that, I'll get 2 times 2, or 4w minus w. And when I subtract that out, it comes out to be 3W. So in this particular case here, as you're going through this turn, you're going fast enough so that basically the scale reads 3 times your weight. And again, that's dependent on what your velocity is. If you look at this equation here, right, you could have all sorts of things for that normal force. You could, if your velocity was less, you could actually have these two cancel. So normal force was 0, right? And so it totally depends on that velocity, which we found through the conservation of mechanical energy. All right, hope this helps.